Hi, everybody. It's a pleasure to work on neural network verification for power system operation. Many thanks to Fran Lee for inviting us in this session. So my name is Spyros Chatzivasileiadis. I'm an associate professor at the Technical University of Denmark, DTU. And this is a joint work with my student, Andreas Venske. What is the motivation behind this work? As you have might have heard, electric power grid is claimed to be the largest machine humans have ever built. So there is actually over the past few years, with a high interest in machine learning applications, there's an explosion in the number of methods applied on power systems because these kind of methods can handle a very high complexity extremely fast. So we see, for example, approaches about neural networks, deep neural networks, reinforcement learning, deep reinforcement learning. And indeed, most of these methods show an impressive computation boost, for example, for the security assessment of the power system. So it seems that these methods can actually perform a security assessment 100 to 1,000 times faster compared with the conventional methods. However, there's a big but. Power systems are safety critical systems. So a power system operator will never trust a black box to estimate if a specific operating point is safe or unsafe, right? So what we're trying to do with this work is we're trying to derive or develop neural network verification methods. This means we try to extract guarantees about the behavior of the neural network. This is going to make the neural networks no longer be a black box, and it's going to build the trust in the operators so that we can at some point see this kind of methods getting adopted inside the control room, okay? So as a guiding example over this talk and in the paper that we have published, we use the power system security assessment. If you go and see in the literature, then all these papers actually have these three main parts that I have here. So first, we need data. So have a database of secure and insecure operating points that can have any combination of a static and dynamic security criteria. So N-1, small signal stability, or many others. Then using this database, we train a neural network. So we encode all this information into a neural network. And then in real time, we use this neural network to very, very quickly assess if a previously unseen operating point is secure or insecure, okay? So first, I'm going to talk about the three main challenges that this neural network verification addresses compared to the conventional, let's say, use of neural networks at this point. First of all, as we have seen, although neural networks for power system security assessment or optimization has been shown to be very, very fast, they will not be adopted in power system operations, in safety critical power system operations, if there is no guarantee about how they behave. So the way that this performance or the assessment of the performance of these neural networks has taken place up to now was purely statistical, right? So we have a test database. So after we train the neural network, we enter these test samples inside the neural network, and we assess how many of them are classified correctly and how many are not. So for example, if you get a 98% performance or accuracy, this means that 98% of the test samples have been classified correctly. However, these are all discrete samples, right? There's no guarantee that any other sample that we haven't included in the test database will be included maybe otherwise. And maybe all the other samples that we're unable to include because we're talking about an infinite number of samples, right? They might actually, in reality, have a very, very bad performance. So the challenge number one that we address with neural network verification is that we can now guarantee the output of the neural network for a continuous range of inputs. So I can tell you that for a continuous range around the reference point, a continuous region around the reference point, the neural network will classify this region as secure or as insecure, okay? Challenge number two, as we said, the accuracy evaluation is highly dependent on the test database. So besides having just discrete samples, what we also overcome with this kind of methods is that we don't really need training or test samples to assess the performance. We can now actually, with these rigorous methods we define, we can assess or we can guarantee the performance for the whole input region without being dependent on 10 samples that might not reflect accurately the real life conditions, right? Sometimes if your sampling or your database is not of high quality, you might not get the results you need. You might not get results that actually reflect the actual performance of the neural network in reality. This doesn't happen with neural network verification. Challenge number 3 is adversarial examples, which is very crucial for safety critical applications like power systems. If you're not familiar with the term adversarial example, these are actually small perturbations around a given input that lead to false prediction. And I'm borrowing an example from image classification. So here you can see a panda. I add a very, very small noise, right? If with a naked eye, you can still say that this is a panda. However, the neural network thinks that this is a gibbon, while it classifies correctly that this is a panda. So this is an adversarial example. If you wonder what a gibbon is, this is a gibbon. Up to this point, the only way to identify adversarial examples has been very heuristic, right? Randomly actually trying different types of noise and seeing how the neural network reacts. Here we actually show a systematical way to identify the adversarial examples for the first time. Okay, so this is the overview. So these are the steps that we will follow, and we're going to describe in more detail in the following slides. The first is that we have to convert the neural network to a set of linear equations with binaries. So we're going to show how we do that. This is a crucial step, and it's actually the key enabler for doing this kind of neural network verification. After we have converted the neural network to a set of linear equations with binaries, this is actually an exact transformation. We formulate optimization problems, mixed integer linear programs. We solve them to zero duality gap. And this actually provide us with certificates, with guarantees about how the neural networks will classify different input regions. Right? So after we get the guarantees of how the neural network will behave, we have to assess if this classification does correspond to the ground truth. So we have to compare the ground truth classification with what the neural network outputs. I'm going to discuss two different optimization problems. The first is I'm going to get a reference input X, and I'm going to guarantee that in a distance epsilon from this reference point, so for this whole continuous region defined by that, the neural network is going to classify all these points are safe or all these points are as unsafe. The second problem I'm going to describe is I'm going to identify the minimum distance from a reference point X where the classification changes. If the classification changes within a short distance from point X, this is an indicator that either we're very close to the true security boundary, or this is an adversarial example, okay? So let's go first and see how we convert a neural network to a MILP. So as you all know, the neural network is described by a set of linear weights with nonlinear activation functions. The most commonly used nonlinear activation function in the recent years has been the ReLU activation function. ReLU stands for rectifier linear unit. This is nothing else than for all inputs that are negative, the ReLU outputs a 0. For all inputs that are positive, the ReLU outputs whatever the input is, right? So I can express this whole operation of a linear weight and the ReLU into a max operator with a linear expression side. And then if you're familiar with optimization or operation research, I can directly convert that in an exact way to a set of linear constraints with binaries, right? And then I can include that to a MILP. So this is how this works or looks like actually. So I have encoded the operations of, I give an input to a neural network, I get an output. I have encoded all this to a set of linear constraints with binaries. Okay, one binary for each neuron that we can then later find ways to simplify that. But the standard way is that there's one binary for each neuron. So this is an exactive formulation. So I have encoded all operations that happen inside the neural network to a set of linear constraints with binaries, and then I can encode this whole neural network behavior, if you want, into an optimization problem. So before going into the first optimization problem, one more point or one more slide that's going to be useful for the next slide. First of all, what's the input? The input for our problem, that's a power system security assessment, is the active power set points of generators, okay? So this is the input. The output is a binary classification, safe or unsafe. So we have a 2-element vector here because this helps us have better performance for our neural network. So if y1 is larger or equal to y2, then we're having a safe classification. So this denotes a safe classification. If y1, if one element is smaller, if the first element is smaller than the other, then we have an unsafe classification. Okay. Let's go define the first problem. Here we assume a given input xref here, and we want to see if the classification within a distance epsilon here, right, from x reference changes, right? So what we're trying to, so we have defined now this region, and we try to see if the classification changes. This xref has a safe classification, so y1 is larger than y2. So we try to see if we try to maximize y2 minus y1. If this becomes positive, right? If y2 is larger than y1, if this becomes positive, this means that the classification changes. If this remains negative, then this is certificate. If this remains negative, this means that all the points inside this region are classified as safe, right? By doing that, I can go now and pick different reference points. I can pick different epsilons, and by that, be able to cover the whole input region and classify it as safe or unsafe and give certificates for that, right? And even if I'm not able to cover the whole input region, I can definitely certify the input regions that I have tested. Okay, so let's see some neural network verification examples. So, for example, we would like to find the minimum distance from the zero input x reference where the classification becomes secure. You can imagine that we have a given load level, right? A given demand in our system. This we are using the 162-bus system, and we want to find the minimum distance from xref that we get into a safe point. This means that what is the dispatch that gives us a safe classification. This means that by that we certify that the whole region, we find the maximum region around this xref that is will have an unsafe classification. So you can see that the ground truth, this is actually a metric that we have here, 6.2%. With the neural network verification. So what the neural network did is that it's very close, 65.5%. Around this region has been classified as insecure because right after that point we become secure. Another thing we can verify, for example, is we can determine what is the maximum wind infeed for which the neural network determines a safe dispatch. So we can see here that the actual maximum wind infeed is at up to 92.5% of the nominal wind power of the maximum infeed. The system remains safe, and this is the actual truth. The neural network verification finds that for any operating point that you enter, where the wind infeed is up to 89% of its maximum wind infeed, then this is going to give a safe dispatch. So I can guarantee you that up to 89% is going to classify that as safe, and indeed we compare that with the ground truth, and this is correct. Okay. Now I'm going to the second problem that has to do with adversarial examples. Let's talk a bit more about adversarial examples in safety critical systems, right? So this is also something that's very common into, for example, autonomous driving, self-driving vehicles. So we have here a camera, and we have a machine learning algorithm that is trying to identify if the light is green or not, right? So here it correctly classifies this as a green light. We change only one pixel at a very random point in the image, and now the neural network thinks that this is a red light, right? This adversarial example, so imagine something like that happening in power systems to actually be an unsafe case, that we're going to have a blackout and the neural network thinking that this is actually safe, right? This is a major barrier for adoption of machine learning techniques in safety critical systems. And this is what we try now to remove with this work. So we identify different, we describe a different, or we define a different problem. We define what we're trying to identify is the minimum we get a given, let's say, reference point X that is classified as safe and is truly safe, right? We try to identify the minimum distance from this point where the classification, so the minimum distance epsilon, where the classification for this point X in this region within epsilon is going to change. So the minimum distance where the classification is going to change, this can be either that we cross from the secure to the unsecure space, so to the we cross security boundary, or as this point here shows, these are adversarial examples. So we are inside the safe region, and this point here has been classified as unsafe. This is a systematic procedure to identify adversarial examples, because we get different reference points and we try to identify the distance epsilon for which the classification changes. If the classification doesn't change for very large distances, this means that we're far away from the security boundary, and in that region, the classification does not change. And if in reality also the classification does not change, this means that there is no adversarial example in that region. Okay. So, for example, let's have as an example here, or an additional example, because all these have also been real data from our simulations. So here we have a highly unbalanced data set for the 162 bus system, right? We assess n-1 and small signal stability with this neural network. So we have a database that classifies as safe or unsafe based on n-1 and small signal stability. And only 1.36% of the samples are in secure region. So this is very highly unbalanced data set. This means that the accuracy of the neural network, even if the neural network misclassifies actually all safe points as unsafe, the accuracy will be 99%. This is very deceiving as a performance metric. Okay. So what we do here is we assess the adversarial robustness. We try to increase the distance from the reference points. So we see here a distance of epsilon of 1% from the reference point. This is relative to a relative measure, and here's plus minus 10%, right? So we see that as the distance from the reference point increases, then the classification gradually increases. So this is what the algorithm will tell us, that we have about 3 or 4% of the data have changed classification. Then we compare them to the ground truth, and it is only 1% that is an adversarial example in this case. Okay. This can also help us for uncertainty. So imagine that, for example, we have inputs of power dispatch that are uncertain, for example, a wind infinite. We can see in a range of the wind infinite around this operating point how the neural network will classify, and if it will classify it as safe or unsafe. And based on that, we can also see or assess if this classification we trust or we do not. Okay. So there are a lot of challenges that we also discuss in the paper related to these methods. So there is a lot of work that we need still to do to be able to deploy them in some real control centers. The first of them is tractability. Up to now, we have been able to verify neural networks with 4 layers and 100 nodes at each layer. In order to achieve that, we had to do some weight specifications. So we had to remove some of the weights of the neural networks, maintaining, however, the similar level of performance. We had to do bound tightening. We had to also prune some of the ReLU activation functions in order to maintain tractability. One more challenge that we have now is that at the moment, we should first certify the neural network output, and we should then assess if this output is correct compared to the ground truth. The challenge that we are actually working towards now is to connect this verification procedure with a ground truth assessment. So what we want to do is to develop a verification procedure that will be integrated in the training of the neural network. And by that, we can actually deliver a neural network training procedure that will offer a certificate of performance. This actually gets us away from statistics. One more challenge is that every time we identify an adversarial example, if we want to remove this from the neural network classification performance, let's say, we need to retrain the neural network, and we need to generate more data. We need first to generate more data in the database around the region where the adversarial example has been determined, and then retrain the network. So the quality of the training database is crucial for good performance. Wrapping up, so the neural network verification can unlock a world of new opportunities for practical applications in power systems, as it can remove the barrier for neural network applications for safety critical power system operations. What we have discussed here are ways to certify, so provide certificates of the behavior of neural networks in the form of formal guarantees. And we have also shown how we can systematically identify adversarial examples. Thanks a lot. This is the paper where we describe all these methods. If you are interested in also seeing how we can convert the information encoded in neural networks to a mixed interlinear program, and from there actually capture constraints that were impossible to capture before, then there's a presentation that you can look at available in this general meeting, also online. And we have also done some work on physics-informed neural networks. There is another presentation for that as well. Thank you very much for that. If you have any questions, please do not hesitate to post them, and we'll be happy to answer them. Thank you very much.